Hello, everyone. Thank you for being here. I'm Fernando Castillo, and I'm going to be talking about verifiable computation and multi-party workflows. First, a bit about me. I'm a tech startup founder. I'm currently a researcher at TU Berlin, where I'm also doing my PhD, and I'm also a coffee drinker. So first, a bit about the motivation for this is that we want to create a workflow that uses the input from multiple parties and that all the parties that are involved can trust in each other's works. That would mean then to have trust, verification, and auditability. What could be a specific use case for this? Decentralized physical infrastructure network where you have the individual use for the asset and at the same time, the asset accounting. Let's say we have an EV charger that produces a specific amount of energy every day, and at the same time, it's used to load specific amount for each electrical vehicle. So in an ideal scenario, we would be having only the periodical information aggregated, and every user would have the confidentiality of the use of their asset. So for this, we would need the different properties. One of them would be confidentiality, meaning that only the person or the entity that needs to know about the information would know, and verifiability, for instance, in the example of the accounting, that all the sum on the aggregation of the use is matched up, and interoperability when you have the multiple parties talking to each other. So this could lead to multiple questions. One of them would be, how can the parties then keep the confidentiality in each of the steps? Another question would be, how can the parties do the verification in the whole workflow? So for this, we will have different tools. We will call verifiable computational components. One of them, zero-knowledge proofs, another, secure multi-party computation, and also trusted execution environments. But all of them had its pros and cons. For instance, a zero-knowledge proof could ensure the computation integrity, but we will require that the executioner of the zero-knowledge program know about the inputs, but at the same time, they will guarantee the integrity of the computation and the output of the cryptographical proof they generate. Also, we'll have in secure multi-party computation that the confidentiality could be kept at the same time for the input that's being delivered for all the parties that are doing the computation. But here we will trust that the computation is handled correctly for all the parties that are involved. And in the case of the TEs, we could have the confidentiality for the result of the computation that's executed and for the input that's given to the TE. Because in TEs, you would have not access from even for the owner of the machine that's running the code. But here, we wouldn't have the computational integrity guaranteed in terms of a cryptographical proof, like with zero-knowledge proof, but here we would have attestation mechanisms that are built in the hardware itself. So we have all of these technologies. What would happen if we would mix them together? Then we would create this type of boxes where you would have mixed properties of confidentiality and at the same time the verification of the proofs that they could generate. For instance, if you mix zero-knowledge proofs with a TE, you could guarantee that the data that's being delivered to the TE is only confidential and not even the machine that's running the code could access the information that's being given, and at the same time, you could generate a cryptographical proof of the computation that's being made. And hence, you could generate workflows like the one illustrated here. So this would require a specific setup, but in which we would require to register all the keys for each verifiable components. For instance, if we would have zero knowledge, like secret snarks, we would need to register the verification keys that are being used to verify the computation, and at the same time, we would need to include the previous keys and the current box that we're using for our VCC. So in the example that was discussed before, we would have the electrical vehicle chargers where they could do an anonymization in the authentication process where a user uses the electrical vehicle charger, and at the same time, then we would have an aggregation verifiable computational component, and finally, this could be verified in the blockchain for public transparency and for the tokenomics that this could deliver. So this scheme could also benefit from an update in the different components that are there. And in this case, we would only need to update the registry in which the keys are registered and only do an update in the VCCs that have direct dependency of the previous in the workflow. So what's the vision for this type of scheme is a workflow in which you could have multiple parties working together and each of them having the confidentiality and the trust in each other works. And all of this could be implemented, for instance, in this example that was described before. You could have the electrical vehicle charger on one side and the electrical vehicle on the other, and at the same time, the owners of those assets could be guaranteed that the use of their assets has been correctly computed for accounting terms. But this might sound that it kind of solved, but currently there are a few challenges, especially these 4 challenges here. One is the high or higher computational cost and overhead for composing or nesting. Also, there's a difficulty when using elliptical cryptographical curves because they need to match if you have a composition of proofs one inside of the other. And as described before, this also requires a specific setup that might be difficult or complex to implement with multiple parties. So the current focus for this is the decentralization of electrical vehicle chargers. Thus, we could enable, on a first step, real-world asset tokenization, and at the same time increase the confidentiality in the workflow that users are being put into. So, as other type of application for this type of technology would be authenticated machine learning, federated or gossip learning, where you would require a training on a specific data set that's authenticated, or also we could use this for supply chain certification, for instance, to calculate or compute a full CO2 footprint emission for a specific product, or to generate green hydrogen certificates. Well, thank you very much. I will be around here. Thank you.